I want to thank the organizers very much for inviting me. It's really exciting to be here. I've really learned a lot from the talks, especially the Tom polynomial talks, which I didn't know anything going in, and I've really enjoyed the hyperbolicity talks as well. I want to talk about the hyperbolicity. Air 1, I thought, did a really good job laying out the area, but I'm going to do some of it again because I really appreciated for the talks that were farther from my area, people keeping them lower or down to earth, and so I'd like to do the same thing. But the goal is I want to talk about how there are these two conjectures about general hypersurfaces. And I want to say that one of the conjectures basically implies the other one with a degree bound. So I'll make that precise and describe what's going on. So first, let's let X be a smooth, complex projective variety. And then as Erwan told us, an entire curve is a holomorphic map, a non-constant holomorphic map from the complex numbers to X. So how do I think about an entire curve? Well, I think of the complex numbers as a curve, and so it's a map to X, and so it's some shape like this. And we say that X is a Brody hyperbolic. If it has no entire curves. I want to take a second. So there's a theme in algebraic geometry and in complex geometry and in number theory. And the theme, and this is Lorenzo talked about it a lot in his talk. The idea is that if Kx is big or ample, then X tends to contain few entire curves. And there are many different sort of facets of this prediction. If the canonical bundle is ample, then you expect it to have few rational points. You expect it to have a few rational curves. It's conjectured to control the geometry of these X in a very precise way. Or if negative Kx is ample, then you expect it to contain many rational curves and many entire curves. And there's a huge family of conjectures about this whole phenomenon that I find very interesting. We're going to focus on this one, and we're going to focus on the entire curves aspect of it. I want to do two quick examples to sort of help orient things. So suppose we have X in Pn, a degree D hypersurface. Then the canonical bundle of X, you can use the adjunction formula, and you see that it's D minus N minus 1. And so for a hypersurface of large degree, you expect Kx to become very ample, and the theme is there should be very few entire curves for these X's. And that's roughly what these conjectures I'm going to write down in a second are going to say. Another example, Erwan did this one as well, is if you have X is hyperbolic, and Kx is ample, then if you blow up X at a point, well, what does it look like? You have this big exceptional divisor, which is just a projective space. Like Erwan said, projective spaces have tons of entire curves, right? They have an affine space inside them with tons of entire curves. So this is not hyperbolic, but Kx will still be big. So if you're going to write down a general conjecture about whether things should have, whether having Kx being ample or big, what it means for entire curves, there's some closed subvariety where things can go wrong. At least if you're going to have something that works for all things. And that is what the Green-Griffiths Lang Conjecture says. I'm going to say GGL for Green-Griffiths Lang. And it's that if Kx is big, or ample, big is just a weakening ample, then there exists some proper subvariety S, or sorry, not necessarily a subvariety, some algebraic set containing all entire curves. And so the picture is very similar to this, right? We have our variety of general type, and in a general point there should be no entire curves, but there might be some bad loci here. And we're going to call these bad loci S, and these could have lots of entire curves. But outside that locus, there are no entire curves. And it's interesting to just proving that it's a wide open conjecture for a lot of, like, there's been important work done, but we're very far from understanding this for all classes of varieties, right? The sequence of talks that we're doing is just for general hypersurfaces, and that seems to be like the frontier right now. But there are many varieties for which this is not known. But what it says is for a general point, there's no entire curves. And then you could also ask, suppose you know that through a general point there are no entire curves. What is this exceptional set? What does it look like? What are its properties? What makes it able to have so many entire curves? Are there any questions about this? This is what in some sense, what the sequence of talks is about. All right, there's another conjecture for general hypersurfaces specifically. This is the Kobayashi Conjecture. And the idea is that, okay, even though in general we can't get better than having some closed subset, that for a hypersurface, when the canonical bundle gets so positive and it's a general hypersurface, then in fact there are no entire curves on that hypersurface. And this says, so let's just say precisely, if X in Pn of degree D has and D is at least 2n minus 1, and it's general or very general, then X is hyperbolic. So that it's saying the Green-Griffiths Lang Conjecture, and furthermore, it's saying that the exceptional set is empty. And what we're what this talk is going to be about is saying if you assume this conjecture, or at least a slight strengthening of it, then can you, in a lower dimension, can you show that as you cut with hyperplanes, the exceptional set shrinks and shrinks and shrinks until it's empty? Let me make sure I am actually talking about what I was meaning to say. Yes. Just a quick word. So Erwan laid out a lot of the prior work, and so I won't write all the names on the board again because I thought he did a great job. But these were ideas of Siu and Demailly, and Devereux, Mercer, and Rousseau had a big, the first sort of complete proof of the Green-Griffiths Lang Conjecture for general hypersurfaces. And then Brodbeck had the first proof of the Kobayashi Conjecture. For a weaker degree bound. And then Bercy and Kirwan did the Green-Griffiths Lang Conjecture for a polynomial degree bound, which was a huge improvement. And then they used the technique that I'm about to show you to see the Kobayashi Conjecture for a polynomial degree bound. So the idea, yeah, and let me write the one other thing I wanted to write is what is the idea of this talk? I said it but didn't write it. Is that the Green-Griffiths Lang Conjecture for general hypersurfaces. Like in Pn of degree D, this implies the Kobayashi Conjecture for general hypersurfaces, same degree but half the dimension, about half the dimension. And the idea is what I'm saying, that as you're cutting with hyperplanes, your exceptional set shrinks and shrinks until it goes away. So I've been deliberately vague about the main statement of what it is that I'm proving, and it's because it's not so hard to state. I'm going to do it in a second, but it's just a little bit. It's not literally true that if you assume this, then you get this. You need slightly more than the Green-Griffiths Lang Conjecture. And so let me try and set that up to give you a precise statement for exactly what it is that I prove. This is joined with David Yang. I'll say it in a second, but in case I forget. Right, so here, we're thinking about general hypersurfaces. So let's draw the set of all hypersurfaces here. And we have the universal family of hypersurfaces over the set of all hypersurfaces. Right? I'm going to call U and D. This is the set of pairs point on a hypersurface, comma hypersurface. It's just the general family of hypersurfaces. And if you assume the Green-Griffiths Lang conjecture, what does that mean? Well, that means on each of these hypersurfaces, there's some bad locus that could contain entire curves. And what's the extra little bit that I assume? Yes, I need a little more space to write this. I'm going to assume that they fit together in a family. That all these bad loci together, they like sort of vary together. That they're not like in some like random like Cantor set sort of thing, jumping all around. Like that wouldn't be enough. You need them to fit together in some sort of family. And so let me say that precisely. I'm going to call it conjecture Green-Griffiths Lang plus. And what it just says, there is some bad locus B and D in UND, and it's a proper algebraic subset such that any entire curve on a general hypersurface lies in BND. Right, and so why does this imply the traditional Green-Griffiths Lang conjecture? I'm saying, hey, there's some algebraic subset of the universal hypersurface that contains all of the entire curve. There's some proper subvariety. And so that means if you go to a general one of these hypersurfaces, there are no entire curves through a general point on that hypersurface. Are there any questions about this?
But this is for the general member of the family or some special can be?
The statement that this is a proper inclusion is for, because I'm only worried about the general hypersurface, I'm not so worried about what BND does on some closed subvariety, and I'm trying to finesse that. You have to think a little, like it's a little bit fiddly to get the details of it right.
Some particular fibers, you can be contained in this set.
Yeah, exactly. For the general fiber, it's okay that BND be non-empty. It just can't be the whole thing. The BND cannot be dense in the space of all points and hypersurfaces. Any other questions? And then you can see from this how one might try to prove the Kobayashi conjecture. You just keep shrinking this BND until it has such small dimension that it can't dominate the space of all hypersurfaces. So to show the Kobayashi conjecture, conjecture K, it is enough to show that BND in UND has codimension at least about n. It turns out n minus 2 is enough because we know things about curves. But let's not worry about the plus ones. Let's say it has codimension n. Let's think about that. So we have this map. The dimension of UND is about n more than the dimension of the space of all hypersurfaces. Yeah, or no, yeah, if the dimension of the bad locus is this BND, if this dimension is less than the dimension of all hypersurfaces, if its codimension is at least n, then it can't possibly dominate the base. It has to map to some proper subvariety in the space of hypersurfaces. And so you see a general hypersurface will have no entire curves. Because a general hypersurface has no bad locus. The bad locus is so small, it just doesn't have enough dimension to dominate the space of all hypersurfaces. And so this is what we prove. And so now I should tell you the theorem. And the main realization that David and I don't use anything about, or use very, very little about jet bundles and vector bundles. The techniques are, it's just about Grassmannians. In some sense, what we're saying is that the idea that the Green-Griffiths Lang should imply Kobayashi, it's a property of hypersurfaces. Anytime you have a hypersurface that's where the general one is not swept out by something, then if you have the dimension, then a general one will contain none of it. And we've proved several results of this type. And if you have another property of general hypersurface that you want to say a general hypersurface has none of it, like this technique, hopefully, there's a good chance this technique will work for you. You should talk to me. So let me tell you what the theorem is. It's just abstracting this setting. So it's saying, this is me and David Yang. And so it's saying, suppose for all n, so d is some fixed degree. And so suppose we have a family of these BNDs in UND for all the different n's. And m is an integer. Satisfying, there are two properties. Well, first, if you look at hypersurfaces of degree m, of dimension m, this is a proper continuum. So this is GGL plus. This is saying, hey, the bad locus is a proper subvariety of UMD. So what this hypothesis is saying is, we know that a general hypersurface is not swept out by entire curves, does not have a dense family of entire curves. And then the second hypothesis is that there has to be some sort of these families for all the different ends, they have to behave well with respect to hyperplane sections. And what the basic principle, I'll write it down in a second, the basic principle is if the lower dimensional hypersurface has an entire curve, then the higher dimensional, through a point, then a higher dimensional hypersurface will also have an entire curve through that point. If you have something that's a hyperplane section, the smaller one has the entire curve, the bigger one must also have the entire curve. And so let's write that down in terms of B's and U's and everything. All right, so this is saying if if Px is a point of B, like R, D, and P and X is a linear section of some X, like 1, in some P at some larger projective space, then Px1 must also be that. Right, so if there's if you could have an entire curve through you in PR, and you're a linear section of a hypersurface in PS, then you must then you could have an entire curve through you in PS. And so this property is very, when you use jet bundles, there's some functoriality of jet bundles. You can take your differential equation, you can restrict it down, and you can see that this property is satisfied. But maybe the way to think about it is, if there's an entire curve through a point in the, let me even draw a picture. If there's an entire curve, so we have a little hypersurface X and some point P. And then we have a bigger and it's a linear section of some bigger hypersurface, what do they call it, X1. And if there's an entire curve in X through P, then there's an entire curve in X1 through P. Because of the all right, so now, let me tell you the conclusion. So if you assume these things, then what I'm saying is as you cut by hypersurfaces, the codimension goes up. So then remember BM had codimension 1, and so if I decrease the dimension by some number C, then the codimension goes up by C. Yeah?
The linear section has to be generic or something?
No. Any linear section. You have to decide whether you include smooth hypersurface or don't include smooth hypersurfaces. So, but if as long as the lower dimensional one is like in the realm of hypersurface that you're considering, then it's okay. And so let's just gesture again about why this implies the Kobayashi. Why this? Let's assume this and then prove the Kobayashi conjecture, right? So if we assume the Green-Griffiths Lang conjecture plus, and we try to prove the Kobayashi conjecture, well, GGL plus is saying there exists an M, right? To prove it for some pair MD, such that the bad locus is a proper algebraic subset of the universal hypersurface. So now let's apply this theorem. With C is equal to M over 2. Then, so this says that B M over 2 D in U M over 2 D. This has codimension M over 2 plus 1. Just by a direct application, right? When you cut the dimension down by C, you see that the bad locus, the codimension goes up. And so this implies that B M over 2 D cannot dominate the space of hypersurfaces, which proves the Kobayashi conjecture. How am I doing? Doing great for time. So the proof is short. The paper is 12 pages, and including introduction and references. And so I want to go through, not in all the detail, but in like some amount of detail, how you prove this theorem. And the idea is that you try and realize it's a property of Grassmannian. You're trying to realize things as a linear section of some big fixed hypersurface, and you're trying to see what property, like the hypersurfaces that do contain an entire curve, you're trying to see if you take all the linear spaces containing those hypersurfaces, you want to see what property do they have, and they have to sort of grow as you go up. Let me write that down. So let's let let's take some huge hypersurface in some huge projective space. It's a capital N so that you know it's big. And we're picking our y to be such that y is big enough. Like what you do is you like take the hypersurface you're interested in and pick your y so that you ensure that it has enough linear sections that it includes the hypersurface you're interested in. For hypersurfaces, you can just write this down explicitly in equation. It's not so hard to see. So we have a big dimensional hypersurface, and let's consider the space of n planes through the point P. This is the set of parameterized n planes. So it's a map from P little n to P capital N with like phi is a linear embedding. And P is a point of image. So this is just the space of all n planes through your fixed point P. And so let's draw a picture here. We've got a hypersurface, a huge hypersurface Y, and we have a specific point P and Y. And we're going to take, we're looking at the family of all n planes in this huge projective space. For each one of these m planes, we can intersect it with our hypersurface, and we get a smaller hypersurface. So we have a map, I'm going to call it psi sub n, going from the space of n planes to u n d, right? Our point is P, and then when we intersect with this plane, we get a hypersurface. The reason the map is rational is because sometimes the plane is contained in the hypersurface, and so then it doesn't work. But we at least have a rational map like this. And we're interested in studying this bad locus, B, in here. And we would like to understand about the codimension of this. And so we can just pull back by this map. And when you take a pre-image, the codimension can shrink, but it cannot grow. When you have a map like this, you could do some sort of blow up thing where the codimension grows bigger. But if we take the pre-image of BND and here, and we can show that this is small, like this has small dimension, then this must also have small dimension. Or if this has high codimension, then this must have high codimension. This is just a general property about maps. So if we can show this pre-image has high codimension, so will BND. And so now we've taken a question that's about pairs point hypersurface, which are a little confusing to understand. And we're looking at a question about points in a Grassmannian, which are easier to understand, right? We're just trying to say, like, hey, looking at this Y, which linear sections contain entire curves? And we're thinking about, like, as you increase or decrease the dimension of these linear sections. So let's call, so now we want to do this. We're comparing for several different dimensions. So let's, we know, right, we started with our M where we knew it was a proper inclusion. So we have phi sub M inverse of BMD. Let's call this, I should call it whatever I called it in my notes. C. This has codimension at least one in the space of M planes. Right, because we assumed not a general such hypersurface did not contain an entire curve. And so we pick our Y to be big enough so that there is some linear section that doesn't contain an entire curve. So we know this, and we, what I'll claim, I mean, in general, we'll need to do it this C times, but I'll just do it once on the board for the sake of simplicity. I'm going to claim that if you cut the dimension by 1, I'm going to call this A. I want to say that this has codimension at least 2. Right, I decrease the dimension by 1, and so then the codimension in the space of, in the universal space went up by 1. And I claim that this claim, it follows from, it's just a general property of linear spaces, right? If you have a family of linear spaces and then you take all the linear spaces that contain it, I claim that just naturally decreases the codimension. So let me state a clear proposition. So proposition, we have, before the proposition, I have to say what they satisfy. this is going to be property star. And the thing is, if we have a linear section that contains an entire curve, an m-1 linear section that contains an entire curve, and then we have some m linear section that contains this m-1 linear section. This means that C also has to contain an entire curve. Like if you have a smaller linear space that contains an entire curve, and you take a larger one containing the smaller one, the larger one also contains an entire curve. So these families, what we do, like one way to look at it is we're taking all the m-1 planes that contain entire curves, and we know that all the m planes containing them has to contain, they also have to contain entire curves. And that's the only and that comes from property 2, the assumption 2 of the theorem. And that's all I'm going to use for this result. So the proposition is let A in GP m-1 n and C in GP mn satisfy this star. Then the codimension of C is at most the codimension of A-1. And that's what you need. As you cut the dimension by 1, the codimension goes up, or as like I just stated it in the reverse order. The proof of this is elementary. It's just a dimension count. I'll maybe draw out the diagram and sort of gesture at it, but maybe I'll spare you the details of the kn+1, kn minus k's. But it's not, the only technical part is keeping track of your Grassmannian, dimensions of various Grassmannians. And so the proof is we have our family A, and we have this incidence correspondence, the set of pairs A and C, such that A is contained in C. Did I get, I sometimes flip, yeah, good. So that A is contained in C, we're going to call that I. And then this maps to the space of all C's. These are the m-1 planes. And these are the m planes. And so you just do a dimension count. The fiber, like the fiber dimension here. Well, you fixed an m-1 plane in Pn, and you're trying to figure out how many m planes contain it, it's just capital N minus little m. I should double check that I'm not off by +1 from my notes. Yep, that's correct. But it's just all, like, it's all the m planes containing an m-1 plane. It's an elementary count. And then here, it turns out you can't have, so what are the fibers of this map? We're fixing some m plane, and we're asking what are the m-1 planes contained in it through P. And it turns out you can't have every m-1 plane. Like, if you have a family where for any C containing an A, the C has to be in there, and for any A lying in a C, the A has to be in there, it's not hard to show you get the whole thing. So this map down has to be, so we're in an M plane, and we're looking for m-1 planes in there passing through the P. So that should be m-1, but it's minus an extra 1, because it can't be, this dimension can't be equal. And the minus the extra 1 is that's the change in codimension. And so if you do out the dimension count, which I'm happy to do, but maybe we'll leave until after that. I'll let someone ask me about it afterwards if they counting dimensions on the board maybe is not, I've already gone for a while about this. You count the dimensions and you see that this codimension has to be this. And that's the result. Are there any questions about this? I have something else to talk about for the last 10 minutes, but I'm happy to, this was the focus of the talk. Great, I wanted to just use the last 10 minutes to talk about a different perspective on this question. Or not perspective on the, but a different type of question that I think is interesting in its own right. And that's understanding, it's understanding that exceptional set. Like saying like, are there things we can do to understand what the, to predict what the exceptional set should be based on, if we assume various things. And so there are two results I wanted to highlight in that direction. And the first is with Izzet Coskun. I did something similar. We sort of did a more souped up version of this where we sort of classify when the codimension changes only by 1, and we say if it changes by 1 then you get something, and otherwise it changes by at least 2. And so we're saying if you assume GGL plus for the best possible bound, like right at, like this is the lowest, sorry, the lowest possible, no, I flipped them. D is equal to n plus 2. This is the lowest possible D such that it's general type. So you assume the optimal result for the Green-Griffiths Lang Conjecture in this sort of universal way. Then for, I need to double check the constant. 3n plus 3 over 2. Let's go 3n plus 3 over 2. So for D at least 3n plus 3 over 2, a general hypersurface x and Pn of degree d has any entire curve lying in the locus Z2. And what is Z2? It's just the set of P such that P lies on a line L, and L either lies in the hypersurface or L meets P, meets X set theoretically in at most 2 points. So there's this locus of, right, we have our X. I'm saying, hey, there's this bad locus where in this locus, every point in this locus like is on a line in Pn that meets X in only 2 points. Usually you'd expect it to meet in D points, right? But sometimes the points come together with higher multiplicity. And so if they come together a lot, then there are some point in this degree range, there are some points where they are on lines that meet only in 2 points. And I'm saying that's the bad locus for this thing. So if the Green-Griffiths Lang conjecture in this like family's way is true for the optimal bound, then we characterize exactly what is the bad locus for this D, at least 3n plus 2. And we're saying it's totally determined by the lines.
It doesn't matter what multiplicity that the 2 points.
Correct. Yeah, so it's going to be a union of several components, actually, in fact. So, I mean, bigger bad locus is worse. So and this is a worsening of our result. But yeah, there will be several components corresponding to the different first multiplicities. That's one. So that's one way to make an assumption and see what it tells you. I'm going to talk about one other way where you can make a weakening, like make an assumption, and that sort of hints that the lines meeting in 2 points have some sort of special property. In order to do that, I need to define algebraically hyperbolic. I need to talk about complements, and I'm going to talk about algebraically hyperbolic. So we have a slightly new setting for this one. We're going to work in the log case. So that means we have x in Pn. It's still a degree d hypersurface. And in a second, we're going to do P2. And so we say that Pn, the complement of x, Pn minus x, is Brody hyperbolic if there are no entire curves in the complement. Right, so these are some definitions. This is the definition of hyperbolic for a complement. I also need to say what algebraically hyperbolic means. We say that Pn minus x is algebraically hyperbolic if the idea is high degree curves have high genus. So if there exists some epsilon greater than 0 and some like hyperplane class H, such that for all curves C in Pn, we have 2g minus 2 plus the number of intersection points of C and X is at least epsilon times the degree. So I mean, you can read the statement. What's it saying? If the degree is big, then either the number of intersection points is big or the genus is big. And I won't go into details, but Demai showed that this is a weaker property than this. That if you are hyperbolic, then you satisfy this, and he conjectured that being algebraically hyperbolic is equivalent to being Brody hyperbolic. But I mean, it would be a difficult, a spectacular, difficult result to show this. But like as we're trying to get intuition for what should these exceptional sets be, it makes sense to try and show this property, which is easier to work with, and then try and like get insight as to what should be happening for this. And so in the last 2 minutes, I want to tell you what happens for very general quartic plane curves. And so the theorem, this is with Shi Chen and me, and then my she's graduated now, but my former PhD student Warren Young. And it's saying if x in P2 is a very general quartic plane curve, then for any curve C in P2, we have 2g minus 2 plus the number of intersection points is at least 1/2 times the degree of C. And so you can have, there's an explicit epsilon here. And then, yeah, that's it. There's, oh, sorry. I forgot the whole point of this was to understand the exceptional set. I forgot to tell you what the exceptional set is. So there are, for a quartic plane curve, there are some loci that you have to rule out. If you have a quartic plane curve will have finitely many bitangent lines. These are lines that are tangent in 2 places, right? You would expect the line to meet in 4 points, and I'm saying, hey, suppose 2 of them come together and then 2 of them come together. So the intersection is like this. This you can see just from the hyperbolic definition. This is P1 minus 2 points that admits a map from the complex numbers, right? that has entire curves. So this has to be in the exceptional set. So these are called the bitangent lines. Similarly, you're expecting it to come together in 4 points, but you expect the line to meet in 4 points. What if 3 of them to come together and then the other one is separate? So you have a line like this, where it meets with multiplicity 3 here and 1 here. This is a flex line, and again, it meets the curve in 2 points. It cannot, this has to be in the exceptional set of the Green-Griffiths Lang Conjecture. What it's saying is, this is true unless C is contained in the union of the bitangent flex lines. And so again, this is saying like, hey, there's something special about lines meeting in 2 points that like is sort of controlling hyperbolicity. And so if one is studying the exceptional set, that's a good characterization. Thank you.
You still have a few minutes?
I still have a few minutes.
Because we started at 10:50.
10:15. Oh my goodness. Well, I was hustling. Well, I'm happy to tell you about. I thought it was a. Well, I'm happy to tell you about more. But I can also stop here. This was
As you want.
This was a natural stopping point.
Okay.
Well, I'll take maybe. Oh, I hate to leave you wanting for talk. Let me say one. I don't think it'll take the whole 15 minutes, but let me say one more thing. To just sort of tie up the case, like if we're studying algebraic hyperbolicity, I want to tell you which hypersurfaces are known to be algebraically hyperbolic and not, and then maybe I'll stop. Right. So I wanted to talk about this because it was more recent work, but you could also ask. For the compact case, what's known about algebraic hyperbolicity of hypersurfaces? And again, this is helping us predict. Like the Beresy-Kirwan bounds are polynomial, but they're like much bigger than which is a huge improvement over the exponential that was known before, but it's still not the same as the linear bound, like the n+2 that we expect it to be. And so you could say what should be true for these hypersurfaces of degree d and Pn, where like when should they become truly hyperbolic, that sort of thing. And so I need to define algebraically hyperbolic for a compact thing. So if x and Pn is, we say this is algebraically hyperbolic. If there exists an epsilon such that for all curve C, 2g minus 2 is at least epsilon times degree. What this is saying is if the degree is large, then the genus must be large. It's like the condition for the log case, except easier, right? You have to lie in the hypersurface, so there's no notion of meeting the hypersurface in a log points. It's a well-known fact that if you have x and Pn, hypersurface of degree d at most 2n minus 3, then x contains lines. Right, so if you can, lines are rational curves. If you contain lines, that means you have lots of entire curves. So the locus of lines has to be in the exceptional locus. So if you want to be hyperbolic, the best you could hope is d at least 2n minus 2. And so there's a theorem. It's due to a lot of people. The closer you get to sort of the threshold, the harder it gets. The less positivity you have from the D, the harder it is to show something like this. And so, like Ein, Voisin, Pacienza, Clemens-Rahn, Coskun and myself. My graduate student, Warren Young. I'm probably forgetting someone, but and then the most recent result is by Abe. But let's just talk about when are they algebraically hyperbolic. So if n equals 3 and d is at least 5, this implies algebraically hyperbolic. Where the last case of d equals 5 was me and Izzet, but Voisin had gotten all the other cases for Shu is someone else I should mention, who had also gotten all the other cases. And for d equals 4, that's a K3 surface in P3, and K3 surfaces are well known to contain many rational curves. So you couldn't be algebraically hyperbolic for those. If n is at least 5 and d is at least 2n minus 2, this implies algebraically hyperbolic. Where that last case was picked off by Warren just I think within the last year. It was in her thesis. And then so for n equals 4, if you have d at least, so it's 2n minus 1, so that should be 9. This implies algebraically hyperbolic. Or I'm worried no, 7. But for n equals 4 and d equals 6, that's not known. That's the only example not known of a hypersurface where it's a very general hypersurface. It's ambiguous whether it's algebraically hyperbolic or not. You can also suppose you allow an exceptional set, and you say like, hey, we're so interested in results like that, where we allow an exceptional set, but you have to characterize the exceptional set. And that's so. Coskun and myself, this is in the roughly the same technique that I was telling you earlier, but if you have a d is at least 3n plus 3 over 2, and your exceptional set is equal to the union of all lines. That's good. And then quite recently, Abe, or within the last year or two at least, Abe said for d at least something like 7n over 5 plus some constant, with S equal to the union of all lines and conics. Right, so in this range. But what this is saying is that, hey, the exceptional set looks to be controlled by the low degree rational curves on these hypersurfaces. Thank you, I'll end there.
Any questions?
Yeah.
How do you prove this theorem?
Yeah. So it follows some of the, there's a roadmap sort of outlined by Voisin. I lost my chalk. Voisin and Pacienza and Ein and that whole list of people. So I'll sort of I'll sort of gesture at the setup, which is hard but not new, and then I'll try and explain the part that's new. So you have to control this, you want to control the degree of the log normal sheaf. If you note, like, the degree of this sheaf is equal to 2g minus 2 plus the degree of c, or minus degree of c. No, that's it. 2g minus 2 minus the degree of c. No, plus the number of intersection points. I knew I was missing something. And so if we can provide a lower bound on this, so if this is bigger than something, then this is the form we want, right? So we want to bound the degree of this sheaf. And so using, if you, this was in Pacienza, if this normal sheaf fits, if you like set up like a universal family of curves, there's some setup, you get a sequence like this, where this is dominated by a bunch of these Lazarus-filled bundles M1. M1 is it's just the it's omega p2 twisted by 1, and we're restricting everything to C. And so we're interested. And this is dominated by a bunch of M1, so you get a map from M1 to this. I know this is big, but just sort of assume you have something like this. You have a map from M1 to here, and that was roughly known before. And so what we're doing is we're studying the stability of this M1. If M1, like, what is the degree here? The degree is negative the degree of C, and this has rank 2. And so if this is stable, if M1 is stable, meaning it doesn't have a quotient of very negative degree, then this cannot have very negative degree. And so it gives you a lower bound on the degree of about 1/2, and that's where the 1/2 in the theorem comes from. If it's unstable, that's bad, but this splitting the instability, it's like an intrinsic property of C. And so you can use a technique of, you have to vary it, but you can sort of, add to a technique of Pacienza, and you can show that, in fact, the only possibility is that your curve it's the curves here that as you vary the line where this is fixed in modulus, it's the curve traced out as you vary along the lines traced in modulus. So like you get like an explicit classification of which curves could have this very unstable and the destabilizing quotient correspond to the normal bundle. You get like an explicit geometric characterization, and then you have to check that those curves are, you just check the genus and degree of those curves.
Other questions?
That we can thank the speaker.